Hello, my name is Lorenz Treitler and I've recently finished my master's degree in cartography and geoinformation at the University of Vienna, and I'm currently working for the real estate database Explorer. In this video, I'm going to talk about the clustering of spatial data, how time can be treated when clustering spatio-temporal data. I will give an example of clustering real estate prices in Vienna, and then I will talk about the multidimensional spatio-temporal change DB-SCAN algorithm to cluster spatio-temporal data. Spatial data can be clustered using standard techniques, meaning that data is being grouped using the attribute values, or by performing spatial clustering, which is grouping by the locations or areas of the data. The third type is regionalization, and also the term spatial clustering is used here, but here it differs from before as it involves the clustering in 2 dimensions or co-clustering, because this now involves grouping by attribute values and space. Spatio-temporal clustering is another type of co-clustering, meaning that data is again grouped in 2 dimensions, but now space and time. The last type is spatio-temporal attribute clustering, which involves grouping in 3 dimensions or tri-clustering, and these are space, time, and attributes. This last type is the least researched clustering type, and there are the least developed techniques that can be used for this type of clustering. But one of these techniques is the multidimensional spatio-temporal DB-SCAN algorithm. As input, it uses spatio-temporal data with an additional attribute, and it is based on a density-based clustering algorithm. As parameters, it takes the spatial threshold that is used for clustering in the dimension space, the temporal threshold that is used to group in the second dimension, which is time, and the value threshold of the attribute. And the last parameter is the minimum number of points per cluster. So therefore, it can perform clustering in 3 dimensions. So time can be used as an additional dimension when clustering spatial data. However, this might not be optimal depending on the clustering purpose. As an example, we have multidimensional spatio-temporal event data, and we want to create homogeneous but not overlapping regions. Time is an informative component, but there is also an evident temporal trend in the data. For example, the values of the attribute we are measuring are increasing over time, and there might be a lack of data to connect the values from the beginning and the end of the time frame. And in this case, the blue points will be separated from the green points as different clusters, whereas these 2 clusters will be overlapping regions. On the next slide, you will see a specific example of that. This graph now shows the development of prices of newly built dwellings in Vienna from 2018 until 2022. You can see an increase in purchasing prices of dwellings in Vienna in this time. There are some mild variations, but overall there is an increasing trend over these 5 years. If we look at the locations of these dwellings, we can also see spatial clusters. So there are some regions with higher values more close in proximity together, and other regions with lower prices. So there is a spatial pattern and also a temporal trend, and we can also see that if we, for example, divide the data by districts, so by different regions, we can still see an increasing trend, but this increasing trend differs between the different regions or districts. So we want to cluster the purchasing prices of dwellings in Vienna. We want to create submarket areas with similar prices, and we want to consider time and want these submarket areas to not be overlapping regions. In this case, we could use the multidimensional spatio-temporal change DB-SCAN algorithm. It reduces the problem of spatially overlapping clusters by considering time as a valuable component rather than a restriction or a third dimension in clustering. It considers the linear trend of values in spatial regions over time, And the parameters are a spatial threshold, a value threshold, which is considered for the temporal trend, and I'm explaining this in a moment, and a minimum number of points requirement, and also the number of runs for the algorithm. This figure shows the steps of the multidimensional spatio-temporal change DBSCAN algorithm. The first step is a random selection of the initial point I. The second step is the spatial clustering of this point and identifying the neighbors. The third step is to apply a linear regression to the point and the neighbors to make predictions for the attribute values and calculate the residuals. If the predictions are below or beyond the value threshold, which is the gray area, then these points are excluded, as you can see for the gray point, for instance. After this, the second and third step are applied to all the neighbors and their neighbors until no neighbors are detected within the spatial threshold value. These four steps are then repeated for all the points until every point in the data is assigned to a cluster or is classified as noise. This clustering algorithm was applied to the transaction prices of newly built apartments in Vienna, and here we can see the clustering results. Every cluster has a different color, and the black points represent noise. The clustering results have also been geoprocessed by census districts, which are the white lines you can see, in order to delineate submarket areas for Vienna. The multidimensional spatio-temporal change DBSCAN algorithm considers temporal trends in the data, which results in fewer or not at all spatially overlapping clusters. It could also be applied and explored for other kinds of spatio-temporal data, such as, for example, in epidemiological or criminological studies. Further development of this algorithm would be to include and test other regression types in the exploration of attribute value change over time, when linear regression is not a suitable choice. Thank you for watching the video on the multidimensional spatio-temporal change DBSCAN algorithm. If you would like to know more about this clustering algorithm or about the work of the Digital Geography group, please read the description below.